thank you, Mario. I will speak from here without a microphone because I'm too close to the receiver, and we just found out that the microphone actually interferes a bit with the receiver. So, sorry, move down here, otherwise we cannot move. Okay, so what I'm trying to do from here is just show you this demo setup here, in which you see SR-DVB transmitter, which is the laptop down here connected to that SRP, which has been demoed in here just 2 years ago at WSR-08. Here we just demoed this real-time SR-DVB modulator while receiving its transmission by means of hardware receiver. Now we're trying to do this with a software receiver. We will show you first the signal being received by a small hardware receiver, which we connected to the beamer, which is this one here, this little receiver down here. So now if I switch source and we give a setting to the beamer, to this, we see this image down here. We have this multi-channel transpose stream, which is composed of channel, I think this is 3. No, okay, channel 2, this one, which is me working with something, I cannot remember exactly what. Then there is a rugby match from last year. Then you have this TV show here on channel 4, and then you have first channel which we were seeing, which is this channel 3 here with a cycling competition. This tells us that we are receiving currently well, 11.612 megabits per second transport stream, standard modulated in SR-DVB-T with SR-DVB-T transmission technique, as long as we are doing this with an ordinary chipset. So I switched back the system to the computer screen, and now we have a software receiver. Okay, we just hooked the signal. You can see here the bit error ratio, which is constant 0, and we just put down here the transport stream. This file is generated live by this process here and contains a transport stream containing the 4 channels. We will only see one channel. I cannot tell you which because EndPlayer, which just reproduces the channel, just chooses the first channel, the first bit which finds within the transport stream. So this is an aggregate which is worth 11.612 megabits per second, which is being demodulated live this way by this software receiver, which you see here. And this is the file that it generates, and we are just seeing live as live transmission demodulated by a fully software receiver. I can show you another interesting thing. If you're used to top process analyzer, you can see that we are doing this by taking roughly 1/2, actually a bit less than 1/2 of the available computing resources. This is our processor, this is our process, which is called SR-DVB, USRP, which is taking 200%, 183% of the CPU. In the language of top, which is this utility here, means that on a quad core, we're taking 1/2 of the computational resources that you have available. And we also have EndPlayer of them. This is not relevant. The thing is that we're doing this at 11.612 megabits per second, and we're doing this real time. We're doing this with no DSP, no FPGA, but just on a standard, really, really standard general purpose processor which you can buy off the shelf. So, okay, have a little buffer. So how this thing is actually possible? I think I'll just get back to here. Okay, just wait for a moment. Okay, great. So this is not a presentation about NN, which is a technique, which is the enabler technology for our system. But I just do feel that I have to tell you something about how is it possible that we do this kind of modulation with this kind of computational cost on that machine there. Explanation for that is this. We call this technique memory acceleration. Memory acceleration actually is an SDR implementation technique, which is aimed at accelerating signal computation over general purpose processors, over DSPs, and we do think, even if we are not yet so sure about this, even over FPGAs. But this is just, let's say, between parentheses. So It belongs to the class of optimizations which has been known since long in computer science as a space-time trade-off. So just get this. But there is a rationality behind MA. If you consider that a 2 GB RAM module runs on 4 to 6 volts or something like that, averagely, and if you consider that a CPU, the average CPU, will instead require, depending on clock frequency and number of cores, from 90 to 140 watts, then you have an implication, very strong one. Implication is this: if used as a computational set, if we have a way of using it as a computational set, memory is a tool which can dramatically increase power efficiency and therefore also, depends on what you choose, computational capacity of such a system, typically on general purpose computing systems, which is the target of our implementation. Memory is mostly, we say, converted commas, unused in current state-of-the-art SDR implementations, because of course, well, memory cannot be unused, but it is not used fully. I mean, the typical implementation, the typical SDR implementation, relies a lot on calculus resources, typically saturates calculus resources, and uses memory only for storing intermediate results, for the physiological needs of the signal processing algorithm that you are implementing. But we can do more. SDRs are something really cool. I actually do love SDRs. But there is a problem with them. They are insanely, we all know about this, they are insanely power inefficient when compared to their hardware counterparts. If this was not true, then we would have a reference implementation, let's say a C++ implementation of a given system, which is the same thing directly as an already market deployable solution. But it's not like that, because these things just do take lots and lots of power to perform a given computation. So why is hardware implementation so much more power efficient than our software radios? It's simple. For each and every clock edge which you have into your radio system implemented in hardware, lots of things can happen. You have so many subsystems which are working in hardware. This is power efficient. So it's kind of a different thing, but the rationale is the same as what you do when you add cores to a general purpose CPU to have more computational power instead of raising clock frequency. If you raise clock frequency, you have significantly more computational power and a lot more of power demand. If you instead add other cores, you're significantly more efficient. So what? Well, MA, what we call memory acceleration, is an optimization technique which provides to a general purpose processor-based software implementation a kind of advantage like this. It actually produces this kind of effect by specializing the memory space. It actually aggregates operations by specializing the memory space. For any single computational act, you do a lot more equivalent elementary operations than you would do if you only were using calculus. And this gives us a highly significant increase in power efficiency over general purpose computing systems. So MA, what we call MA, has a design flow. It takes a traditional calculus-only implementation, either on paper or a running reference implementation of, say, a given radio. It applies to algorithmic tools which are called RTAR, Recursive Table Aggregation Algorithm, and AES, Algorithm Segmentation, and finally returns a memory accelerated implementation which will typically run about 10 times faster for our current research status in MA than the original implementation. This is still a very ongoing effort, so 10 is our current factor. I cannot really tell you how big this factor might be in the future. So just to quote a few, the best obtained acceleration factors by using NA on some subsystems, which are all into the implementation that you have seen right now. The OFDM timing and frequency offset estimation, known as the Morrison algorithm, which is what we are using right now to produce timing and frequency offset estimation for our OFDM symbols, has been accelerated by NA by a factor of 12.6.